Hello everyone, I'm Mac Design from Stroud Research Center. Today I will be talking about Part 2 of the load calculator process. Part 1 started off talking about the different ways you can calculate sediment and chloride loads in the load calculator. It then concluded with how to enter your data-rich rating curves into the load calculator to start the process of sediment and/or chloride load analysis. Today I will go through the extensive process on how to locate and prepare sensor station data to analyze the storm event. With all of our rating curve equations entered, we'll now obtain sensor data to look for storms that we want to analyze. There are three ways to get storm data from your sensor station. The first is going online and go into the Monitor My Watershed portal using this URL. When you get to the page, click on Browse Sites. It will be greeted with a big map with a bunch of different sensor station locations. You can either find your station by entering the name of your organization or by manually panning and scrolling until you get to the station you want to get the sensor data from. Click on the dot that represents the station you want and hit View Data for this site. You'll be greeted with a home page of your sensor station. Scroll down until you see Download Sensor Data and click it. The second way is going to the DreamHoster's data portal. This one is designated through logger numbers and the name of the creek that your station is found on. You can scroll down until you see the logger number or stream name that corresponds with your sensor station. Then you click on the title and you will be greeted by a different home page. Click Get Raw CSV text file to get your data. The last way is for people who do not have online capabilities for their sensor station. This is by downloading your data from an SD card by going to the site. There's a separate video about downloading data from the sensor station and uploading it to your computer that I have provided. Please refer to this video if you do not know the process of going in field and getting sensor data. Any of these choices will require the data to be saved as an Excel workbook, because either they'll be as a text file or a CSV. To do so, go find your downloaded data and then double click on it to open it. For a text file, you would want to right click and choose to open with Excel. You'll be greeted with a page, in this case with a CSV file, and you'll see a raw data of your sensor station. To save as a workbook, hit File, Save As. Choose your location of where you want to save the data, and under Save As Type, hit the down arrow and choose Excel Workbook, and save. Once your data is saved, you will need to visually analyze it to see what storm you would want to use in the load calculator. The best way to do this is to graph your downloaded data in chunks within the saved Excel workbook. This can be done prior to using the load calculator when downloading data from your sensor station on a minimum quarterly basis as a data QC. You could use the online data streams as a visual help, but time zone conversion will be necessary to properly line up the downloaded data with the data stream visuals provided by Monitor My Watershed or DreamHosters. For this reason, Stroud's staff heavily encourages the first option of graphing the downloaded data and will carry out this option in the video. First, open the Excel workbook that contains your recently downloaded sensor station data. Scroll down a bit until you see the data streams itself, and then begin to extend your columns to read both the data and any headers that are obscured from view. Next, we'll designate one of the tabs below as an area to put a chart. Now we'll insert the chart on this worksheet. To do so, go to Insert and go to Scatter. Hit that down arrow below it. There's a few options that you have. You have just data points with smooth lines, just smooth lines, data points with very sharp lines, or sharp lines. Now, the data stream comes in as a smooth line without any data points, so we want to choose Scatter with smooth lines. Drag the chart up to the top left corner and then increase the chart space to fill up the worksheet. That way you can see it a little easier. With a new blank sheet, right click on it and then select data. This will open up a data input window. This is where you can add all your data stream into this graph. To start, go to Add. This will make a new data line for you. Designate this series as Depth, and then hit the button to the right of the blank row. This will begin to import our data. Go back to Time Series Results and choose the data under Date and Time. Hit the first data point and drag all the way down. This is where we would suggest that you want to do it in small, tiny chunks. I usually do it, since we do a quarterly basis of SD card downloads, I usually do 3 months worth of data. It might be even easier to pare it down to about a month to make this type of process go quicker. As it approaches the bottom, it will slow down until you get a temporary stop at the last point. Make sure that point's highlighted and then release. Hit the button to the right and it'll plot your X values. Now we'll do the Y values the same way. Click the button and it'll actually automatically scroll you back up to the top of the columns, and then choose the first data point under Depth and then begin scrolling down again. This is a drag and hold method, so be sure not to release your left mouse button until you get to the very bottom on the very last point. Okay, it slows down again, and then we go to the last point. Then click basically an upload button. So now you should have the name of your data, your X values, which should be a time series, and your Y values, which should be the sensor values. Hit OK, and it should now plot your depth data. Now we repeat the step for conductivity in both the high-end turbidity values and low-end turbidity values. If you're just analyzing for turbidity, then you just have to worry about turbidity. If you're just analyzing for chloride, then you just have to worry about conductivity. But if you're doing both curves, you want to be sure to have all 4 pieces of depth data, conductivity data, low turbidity, and high turbidity. We now have all 4 data streams plotted on this graph. We have conductivity, depth, and both turbidity values. You'll start taking notice that some of the data streams, usually turbidity data, will appear messy. So an example is right over here, and a little bit in here too. This is usually from environmental interference in the field, such as algae buildup, settling of debris near the probe, and other issues that can affect the accuracy of the probe's ability to measure turbidity. Instances of flatlining will occur in all 3 or 4 data streams depending on what you're plotting. This is usually an indication of a hardware or software issue. During minor instances of these foulings, we can clean up the values via estimating it during the time of measurement. This can occur when there are only single points of spiking or a handful of points of issue, such as here, here, maybe a little here. During major instances of fouling, there's not much that can be done to fix this. If a storm spike is severely fouled, it currently cannot be used for calculating loads, such as here. This is why it's very important to stay on top of cleaning your sensors, checking your data on at least a weekly basis, and even being on site during storm periods to not only just grab samples, but also to keep the data clean if you're able to. From this selection of data, we'll then pick a storm instance or data spike that seems to have minor instances of fouling that we want to analyze. This will take some time depending on how much data you plotted, because it takes a little bit of time to sift through. To slim down the effort, you can focus on data spikes within the turbidity, conductivity, and or water depth streams that were graphed from the raw data. So I'm thinking maybe right around here is where we'll do our first analysis of storm data. To start the process of separating spikes from the main data stream, we want to first figure out our start and end points of that spike. So So we decided that we want to do this spike for analysis. Usually what I like to do is I like to find little depressions on either side of the spikes where it flattens out. So an example would be right here for this spike. I would start here as my start point for analysis, and I would end it around here. For this spike that we want to analyze, our endpoint's pretty easy to find. It'll be right around here. Our start point, I'm thinking, will be sort of in this area right here. Now, when you hover your mouse over the data stream, you'll see a little yellow bubble up pop up that will say what series or line it's analyzing. It'll give the X values, which is the date and time, and it will give you the sensor value for that instance. So since it's depth, it's giving me a depth reading. You want to record this down, the date and time, either on a piece of paper or electronically in a notepad, just so you can mark where to start, and then you can do the same thing for the endpoint. Now before we go on to marking our start and stop points in the time series, we want to insert a blank chart as preparation. So we'll go to Insert, under Scatter, and we'll choose the same type of scatter with smooth lines. Then we'll stretch it to fill the screen just like the above chart. Scroll down a bit. Okay. Now we'll go to our time series data. And now we'll just scroll down and search for our X values to indicate our start and end points. What I usually do is I highlight the row and I'll pick a type of color to fill it with. I usually do a gray. Now I'll do the endpoint. Alright, now we'll fill in all the values in between the start and end points. This way it's visually easier to search for our X and Y values when we have to re-plot our spike. Okay, we'll scroll back up to the top of this section in preparation for inserting our new data streams. Now click here to keep our bookmark so I don't have to scroll again. So we'll return to chart, and then we'll right click on the empty space and hit select data. Click on add, and we'll do our depth first. And this is basically repeating our input of the quarterly sensor data, but this time we're slimming it down to one storm instance. Be sure to take your time because you can blow past the endpoint, just because this is not the end of all the values, so it will not do a slowdown. Now we'll do our Y's. Okay, so this is what it looks like. It's a slimmed down version of the spike being graphed right here. So now we'll repeat the same process of adding data in for our conductivity and our two turbidity values. Okay, so now all four values are plotted. Our next thing to do is to take a look at our newly plotted spike and to see if this is usable to move on to the next step. And the indication of whether it's usable or not is how much fouling has occurred in this spike. And we're only seeing single values that have spiked up just a little bit. So through a process of cleaning up data, we can soften these hills a bit and actually have a pretty darn good turbidity stream that we can actually analyze for sediment load. Now an example of where it might be really messy that we would have to move on to the next spike would be right here. This takes time to learn about data a bit. So as mentioned before with turbidity, it's very raw data. So that means anything that goes in front of this camera lens on the probe will be picked up. So this actually might not be a sediment spike, or if it was a sediment spike, it might not have lasted long or has as big of an impact as is being shown. Whereas conductivity is a little more forgiving with raw data since it's measuring the electrical charge of the water and it's more of a chemistry-based thing, whereas this is more of a physical analysis. So if we did want to analyze this to think this could be usable and we found it to be really fouled, we would then move on to the next spike, which could be here if you just want to do chloride. But if you want to do a combination, I would either choose this one or this one since it lines up. Either way, we chose a pretty good instance, a storm instance to analyze. So now we'll move on to the next thing, which is cleaning up this turbidity data. Before beginning the process of cleaning up fouled data, we have to set up a workspace in order to make it easier for the process, as well as creating a separate data value set from your raw data. That way when you're editing it, you're not editing the raw data itself, you're editing a separate set. To do so, we need to take and copy over our highlighted values that we chose as our spike and throw them in here like how I did here. Be sure to include a header so we can identify what each column is. Then we want to put in a new chart, a scatter plot chart that uses the same appearance, which is smooth lines. And then you want to graph all these values right in here again, just like how you see over here. So what happens is as you edit data here, there will be a real-time change of either reductions or smoothing that you can track your progress of cleaning up data over time. So once when that whole thing is set up, we can begin cleaning everything up. To do so, we'll first hover over our top spikes since they're easier to see that they're fouled. A yellow bubble will pop up, just like how we used to identify the start and end points of this spike here. And we'll use the date and time and even record down what the value is to go look for the point that we want to edit. So once when that's recorded or memorized, we then go down and search for that value. Here it is, and then we highlight the full row. Next, we want to identify that this is an edited value or an edited row, not just a raw value. So once when that is identified, we then need to mathematically correct it. And there's a system for this. What we do is we take the top adjacent value, or like the one that's the biggest, that's adjacent to this one, which would be 112. And we subtract the smaller value then from it. What this does is it creates a range, a data range between the two. So we know we have to go from 1.8 units between these. We then divide by 2. The reason for this is that there's a single line right now that needs to be edited, and it takes 2 jumps to get between 110 and 112. It pretty much is making a bridge almost between these two values to correct it. Or like that's how we are smoothing out our huge spike between the two. So that results in 0.9. What we then is to take that bridge to go from 110 to this value, we add 0.9 to it. So this is our new median number between these two values. And to show you the change, I'll scroll back up, and you can see that orange line that was all the way up here has now dropped significantly. Now there's a corresponding lower turbidity value that's up. That's what we'll have to change as well. So we'll just go right back down till we see that red line pop up. There it is. And we'll repeat the same step with this turbidity value. We'll take the highest of the two, which is the 108, subtract the lowest value from that to create the range. Then we'll divide by 2 to figure out the value step to get from 107 to the new value, then to the upper value. So that's 0.6. Then we add it to the lower value to create our median, which is 108. So that's how we usually do single point spikes or a single point fouling. You can see it's smoothed out a bit. Be sure to take your time with this, and this can take a little bit of patience and messing with it and on some learning curve with this. But this is a very important step before doing our finalized step with the load calculator. This concludes part 2 of the process on preparing and analyzing data within the load calculator. Part 3 will use the sensor station data that we just finished cleaning up for storm analysis within the load calculator. Thank you for watching. I'm Matt Gazzani from Stroud Water Research Center.